If you've ever flipped through an electrochemistry paper, you've probably seen this weird duck-shaped curve, right? That's a cyclic voltammogram. It's honestly one of the most powerful techniques in the entire field. But let's be real, it can look super intimidating at first. So today, we're going to demystify. We're going to grab our chemical camera and learn how to take, develop, and read these incredible electrochemical pictures. The first step to really getting CV is to just stop thinking of it as a confusing graph. I want you to think of cyclic voltammetry as a powerful chemical camera. Seriously, it's a tool that gives us a snapshot, or really more like a movie, of electrons literally jumping to and from molecules right there on an electrode's surface. So here's our game plan. First, we'll get to know our camera, the whole experimental setup. Then we'll learn how to frame the perfect shot by picking our settings. After that, we'll head into the darkroom to develop our picture, the voltammogram itself, and figure out how to read its story. We'll see what the picture's quality tells us about the reaction speed, learn how to change our camera's shutter speed, and finally, we'll flip through a photo album of its amazing real-world uses. Okay, first things first. Before you can snap a prize-winning photo, you've got to know your equipment and your subject, right? Well, in electrochemistry, that means understanding our cell and what exactly we're trying to see. This right here is our camera body, a standard 3-electrode cell. The working electrode, that's our lens. It's where all the action happens. The reference electrode, think of that as our tripod. It provides a rock-solid, stable potential that everything else is measured against. And the counter electrode, that's kind of like the battery pack. It completes the circuit so current can flow, but it does it without ever messing with our main subject.
So what are we actually taking a picture of? We're capturing the exact moment an electron takes a leap of faith. And we do this by sweeping the electrode's potential. Imagine you're turning a dial that changes the energy of the electrons in the electrode. Once you give them just enough juice to jump into an empty spot on a nearby molecule, zing, an electron transfers. That's a reduction. Then, when we sweep the potential back, we're basically coaxing that electron to jump back home. That's oxidation.
All right, just like any good photographer, we have to frame our shot. In CV, this means picking the perfect range of potentials to scan. Your goal is to capture your molecule's reaction and absolutely nothing else. The whole process is actually this beautifully simple triangular wave. We start at some initial potential, we scan at a constant speed to a switching potential, and then we just sweep it right back to where we started. You can literally picture a windshield wiper just steadily going back and forth across a whole range of electrical potentials. Now, here is a super crucial part. You have to stay inside what's called the stability window of your solvent. If you go too far in either direction, applying too much positive or too much negative potential, the solvent itself starts to react. And that creates this massive current that's like a blinding lens flare in your photo. It completely washes out the signal from the molecule you actually care about. Okay, we've set up our camera, we've framed the shot, and we've taken the picture. Now it's time to head to the darkroom and see what we've got. Let's break down the anatomy of the voltammogram that pops out. And there it is, pulled from some real research, the classic duck-shaped plot in all its glory. Don't worry about all the text on there for now, just look at the shape. On the horizontal x-axis, you've got the potential that we're applying, and on the vertical y-axis, you see the current that results. As we do that back and forth sweep, we trace out this beautiful curve, and believe me, it holds a ton of information. The two main parts of this curve are called branches. You've got the cathodic branch, which is where reduction happens, that's molecules gaining electrons. And then you have the anodic branch, which is where oxidation happens, molecules losing electrons. It really is that simple. Now, a quick heads up. You are going to see these plots oriented two different ways, looking like they're just rotating 180 degrees from each other. Don't let it throw you off. It's just a matter of convention. The US, or polarizographic convention, has potential getting more negative to the right. The IUPAC convention has it getting more positive. Neither one is wrong, and the data is exactly the same. You just have to glance at the x-axis to know which one you're looking at. Okay, let's zoom in a little and look at the details of our picture. The shape and the position of those peaks, totally not random. They tell us a really deep story about how fast the electron transfer is happening. It all boils down to a race between two things: how fast electrons can jump and how fast molecules can get to the electrode to catch them. Think of it like trying to fill buckets with a fire hose. If the buckets are all lined up and ready to go, that's like fast electron transfer. The whole thing is super efficient and reversible. But if the buckets are far away and have to be carried over one by one, well, that's slow, and the process becomes irreversible, limited by how fast you can move those buckets. So, how do we know if our reaction is fast? Well, there's a magic number. For a perfect reversible process that involves just one electron at room temperature, the separation between the two peaks, what we call delta EP, is right around 57 to 60 millivolts. This is one of the most important diagnostic tools we have. And this table just lays it all out beautifully. If that peak separation is close to 57 millivolts and the peaks look nice and sharp, boom, you've got a reversible system. As that separation gets bigger and the peaks start to broaden out, you're looking at something quasi-reversible. And if the peaks are really far apart, or maybe one of them even disappears completely, you know you're looking at a slow, irreversible process. Now for one of my favorite parts, and one of the most powerful things we can control, the scan rate. I want you to think of this as the shutter speed on our chemical camera. By changing how fast we sweep the potential, we can uncover completely new information. Just take a look at this. Each one of those curves is a different shutter speed. As we scan faster and faster, going from the inside curve out, notice what happens. The peaks get taller. A faster scan gives you a bigger current. But the really interesting question is, why? The answer is so cool. I mean, what's the mathematical relationship here? Is it a straight line? Is it something else? Because the answer tells us something totally fundamental about where our reacting molecules are actually coming from. And here it is, the incredible payoff. By just running our experiment at a few different scan rates and making one of these simple plots, we can instantly tell what's going on. If the peak current is proportional to the square root of the scan rate, we know our molecules are diffusing, swimming through the solution to get to the electrode. But if it's directly proportional to the scan rate itself, we know they are stuck or absorbed right on the electrode surface. It is an unbelievably powerful diagnostic tool, just hidden in plain sight. So, we've learned how to use our camera. Let's wrap things up by flipping through a quick photo album to see the incredible images this technique has captured all across science and engineering. The applications are just huge. In energy storage, it helps us test new materials for better batteries. For sensors, it can detect tiny amounts of a specific chemical. It's crucial for studying corrosion, for figuring out the hidden steps in complicated reactions. And that's why it's almost always the very first snapshot an electrochemist takes when they get their hands on a new, interesting material. And this quote really brings it all home. As the researchers Yamada and his colleagues put it, even though it can seem complex under the hood, its sheer simplicity in the lab makes it the go-to technique for electrochemists everywhere. It is the essential first look at any new system. So the next time you see one of these plots, please don't just see a confusing graph. See a photograph packed with information and ask yourself, if one clean peak tells a simple story, what kind of complex dance of electrons must be happening to create a picture with multiple peaks?